Okay, yeah. So my talk is a little bit different than Torsten's. So I'm looking more at how to generate recommendations using recurrent neural networks and how to solve a particular problem that arises when we do session-based recommendations, right? So this is not basically, these are my collaborators and actual friends, and this is work we've done together. And basically, the work that I'm presenting here has been published already. These are the 3 papers that we published on it. Session-based recommender systems at ICLR, and 2 improvements upon the same architecture at Rexis 2016 and 17. So what is a session-based recommendation? Many recommendation systems implicitly assume actually, because this is not an explicit assumption, that the user arrives to the system, he receives a recommendation, he acts upon the recommendation or not, and goes away and never comes back, or maybe he comes back next week, takes another recommendation, etc., right? And for this kind of settings, matrix factorization type algorithms seem to perform very well, actually, right? So what actually happens in practice and is very common is that, for example, in e-commerce, a user comes and looks for an item for maybe half an hour and then decides to purchases or not. And during this half an hour, he clicks through various items in the page and receives a recommendation, right? So this is a setting of recommendation that is slightly different than the previous one that I mentioned. And there are things there that we can take into account to improve the recommendations, right? For example, here, one user might want to buy a coffee machine. He starts clicking on espresso machines. Halfway through the session, he changes his mind and decides to purchase a mocha in the end, right? So this is a typical sort of session that you might get. And the data of this kind of sessions look like that. We have a session ID. We might not necessarily have a user ID. So the user might not be logged into the system, right? So in some sense, we are in a sort of permanent cold start situation where we have no information about the actual user that we are serving recommendations to. We might have some kind of timestamp, item ID that was clicked upon, maybe category, and maybe additional information as well, right? And so how do we actually model this data to perform good recommendation to the users? The thing that has been done until now, and actually what Amazon has been using until recently, is item-to-item similarities, right? You can actually check these sessions here and see which items are clicked in the same session often, co-queue in the same session often, and recommend these items when the user clicks on one of these, right? This works well, right? It's a sort of standard method, right? It has been used for many, many years. It's essentially what association rules do, item-to-item similarity using cosine similarity, et cetera, right? But can we do better? And it turns out that nowadays we have this kind of tools to do better. We have these recurrent neural networks, right, that are very, very good in modeling sequence data, right? I'm not going to go into, I assume you're familiar with recurrent neural networks, right? They maintain a state. The state gets updated given the input, and given the state, you have an output, right? And this is sort of the vanilla version of recurrent neural networks here, right? Where here you have the input, here you have the update of the state, and given this input in the current state, you compute a new state. Given the state, you compute an output. This vanilla version turns out to not work very well. People have improved upon this vanilla version RNNs 20 years ago already. We had the LSTM by Jürgen Schmidhuber and Hochreiter. And more recently, we have the gated recurrent units, which are slightly simpler version of the LSTM, right? They're a little bit more complex, but essentially perform exactly the same task, right? Extremely efficient tools for modeling sequence data. And these networks have been used in many tasks in machine learning recently, right? From sequence labeling, document classification, speech recognition, but also in a generative manner, generating text, music, etc. So how can we use this to model sequences? Basically, it's quite simple, right? We one-hot encode the items in the input of the recurrent neural network. In the original paper, we used a GIU recurrent unit. We didn't find LSTMs to perform any better. They performed actually exactly the same, but the GIU used slightly less memory, so we stuck with that. And on the output, we get scores, probability scores for all the items in the catalog, right? And we train, given a session, we try to predict, given the previous item, the next one, right? Of course, you could actually stack several layers of these recurrent neural networks, but we found that actually, because the sessions, or most of the sessions in the data we have, tend to be relatively short, there was not a lot of value in adding more layers. And so we stuck with one layer. And when we first tried that on a vanilla recurrent neural network, we actually didn't get really, really good results. We actually got results that were actually slightly worse than the simple item-to-item similarity type of methods that you could use on this data. So we tried to sort of improve upon that. One of the first things we did is change the way mini batches are done in the recurrent neural network. So you see, these recurrent neural networks assume that you have a continuous stream of data, right? If you have text, that you have several pages of text, et cetera, et cetera. So it's relatively easy to do mini batching there. It's slightly less easy to do it when you have short sequences of data that are sort of independent of each other. So you have short sequences of clicks, 4 clicks, 7 clicks, 9 clicks, right? So the way we did this, so we changed the mini batching and we used session parallel mini batches. Essentially what we do is we stack sessions on top of each other and take the first item of all the sessions as a mini batch, right? And the second item, et cetera, et cetera. When one session is finished, we concatenate, and we add another session here, et cetera, and we continue mini batching in this way. We call this session parallel mini batches, and this already improved upon our results quite substantially. The second thing we did is we typically when you use these RNNs, and most deep learning methods nowadays, they use a categorical cross-entropy loss function. This didn't seem to work very well at the beginning for us. So we replaced that with a pairwise loss function. And there's a whole sort of family of pairwise ranking loss functions that you can use for optimization. But we tried one of the most commonly used BPR, Bayesian personalized ranking loss function. And that already worked quite well. And we slightly modified that. We added here a extra regularization term on the negative sampled items that improved things quite substantially as well. And we called that top one ranking loss function. The way this pairwise ranking loss functions work, just to quickly recap, is you have the item that the user has clicked upon. You sample a negative item, which is an item that the user hasn't clicked upon in that session, and you compare the scores of the model on these two, right? And what you actually want at the score of the item that the user has clicked is higher than the score of the item that the user hasn't clicked, and you incur a penalty when this is not the case. No? And of course, this is a soft approximation of that. So that, of course, creates all sorts of other issues. If you try to run this kind of loss functions over all of your data, and you have hundreds of thousands of items in your catalog, you obviously cannot compare all these pairs, right, of all the items that the user has clicked versus all the items in the catalog. So what you need to do is you need to sample out of this out of this set of items. So there are all sorts of sampling techniques that you can use. What we used is popularity sampling at the beginning, and the way we implemented that is taking the session parallel mini batches. We sample the items that the other users in the mini batch have clicked as negative items for the current user for the current active user. And that's actually a very, very efficient and fast way to do that, to the sampling. Putting all these sort of three tricks together, we actually got pretty good performance. So this is basically the baseline that we were trying to beat, which is the item nearest neighbor method. So just serving similar items based on the sessions. And we beat that quite substantially with the recurrent neural network by about 15 to 30%. We used two datasets, the Rexis 2015 challenge, which was about given e-commerce sessions, predict if there would be a purchase or not. In this case, we discarded the purchase data and we just used the clickstream data, right? And we also got data from a YouTube-like video service. So there the task was basically to recommend during a video session new videos to the user, right? So these were offline data. We actually deployed the system on an e-commerce site. And back then, actually this was last year, back then our implementation was really, really slow based on the HANA, et cetera, so we couldn't really train on all the data that were available or for the recommender system that was already implemented. So we actually trained only on 10% of that data, but we already got uplifts compared to the implemented recommender system, right? So once we finished with that work, we thought, okay, I mean, this was just sort of, let's say, step number one, right? Just take an RNN, train it on the session data, see what happens. It works. How can we improve it? So we thought about, the kind of data we use. When you're actually looking at a website, apart from the item ID, I mean, the user actually doesn't perceive the item ID. What he perceives is sort of the picture here, maybe some description, some text, the price, right? So this is all additional information that you can incorporate into the model to improve recommendations, right? So, and of course, nowadays we also have really, really nice deep learning models that can take this kind of text data or image data and extract nice and rich features out of it, right? So first we thought, okay, let's only train on the image features, right? Instead of using user IDs, one hot encoded user IDs, let's just take a nice convolutional network, pre-trained, pass the thumbnail through it, get some kind of features for the thumbnail, right? For the image we have here, and just use that as a training input instead of the item IDs. No? We tried that on some data from a classified site. Something like eBay from a large European country, and it really did extremely bad. So while looking at the outputs of the model, the outputs actually looked completely reasonable. So if a user was clicking on a car, he was getting recommendations for cars. But still, all the metrics, mean reciprocal rank, et cetera, looked really, really bad. The reason was that, apart from the picture, of course, people also look for particular features in the products that they're using, right? Price ranges, et cetera, right? And if you just use the image, this is not taken into account. So the second thing we thought, okay, this didn't work. Let's just also concatenate the original information we were using in the RNN, right? The one hot encoded item ID. So we have here the one hot encoded item ID and the image feature vector, right? And use that as an input to the recurrent neural network. That worked much better than just using the image features, but it didn't really improve upon the original results that we had, right? For just using the item ID. So the next thing we thought is, okay, maybe we can sort of use one network to improve upon the other in some sense. So we basically separated here the networks, and we used two networks, two recurrent neural networks, separated, that we trained concurrently. We call them parallel recurrent neural networks, one with the item IDs and one with the image features. And then essentially what we do is we join them somewhere in the output, right? In some kind of ensemble learning, right? And the way we train this network is essentially we train one on the residuals of the other. We tried all sorts of different ways. Sort of simple residual training, we fully train one network and then train the second network only on the residuals of the other. Alternated training, we train one network, one epoch of one network on the residuals of one epoch of the other, or interleaving training where we train per mini batch on the residuals of each network. And this seemed actually to work. So we tried this on some data of, again, this video site, where we used image features from the thumbnails. We used GoogleNet to extract features from the thumbnails of the videos. And we got pretty significant lifts, let's see here, about 10% from the naive recurrent neural networks, right? If you concatenate the thumbnails. And here residual training seemed to work best, but more or less the same as the other training networks, training techniques. So we also did the same with text features. And in text features, in text, of course, you can do all sorts of things. Here we did something relatively simple. We just took TF-IDF representations of the bigrams of the text and used that as features for the recurrent neural networks. And again, we got about 3.4% in recall and 5.3% in mean reciprocal rank improvements. This was again the classifieds data. Okay. So once we finished with that work, something else came up. So it turns out that in many of these data sets, the assumption that we have no clue about which user is coming to the system is not always true. Right? So we might actually have some information about the user, or actually we might have some information about some sessions where we know that the user is logged in and has had other sessions in the past. So we might want to take advantage of that, right? So in a sort of, in the naive case, you have anonymous users coming in and having sessions, right? But often, because the user might have a cookie or they might look at some videos here, cartoons, NBA, but often because the user might have some cookie, we might actually know that this user and this user were actually the same, right? So we might want to take advantage of the fact that we know the past history of the user here, right? So we might want to personalize this session-based recommendation. So, and the question here was like, how can we take advantage of this information? How can we incorporate sort of long-term preferences with the sort of short-term preferences that happened during the session. No? And again, one naive way to do that is to just take all the sessions of the user we know about and just concatenate them and feed them to the neural network. Right? And we're going to see this actually does improve things a little bit, but not significantly. The other approach we thought about is basically trying to sort of decouple user and session representations, right? We can actually train here, what we actually do is we train two recurrent neural networks. One that does exactly what the other recurrent neural networks were doing, tries to predict items, recommend items for the user throughout the session. And another recurrent neural network that takes the state, the last hidden state of the previous recurrent neural networks and tries to predict a good next hidden state to initialize the recurrent neural network that does the session-based recommendation, right? So to give you a quick idea here, so basically here we have, let's see. Here we have the recurrent neural network that does the prediction for the session, right? And here, this is basically the initialization of the hidden state of this recurrent neural network, right, for this user. So now we have another recurrent neural network that takes the initial hidden state, right, of the user and the last hidden state of the network that was produced during the session. And given these two hidden states, tries to predict a good initialization for the next session of the user, right? Okay. And there's all sorts of ways to use this hidden state. One is, of course, just to initialize this network. Another way is to actually take this and also use it as an input in all the steps of the user, right? Sort of enforce it as a sort of context, if you like. We call this hierarchical learn and all. And once you're done, of course, you repeat the process, right? You take that hidden state and the last that was produced here and use and do a prediction for the next session of the user. In that way, actually two identical sessions of two different users that had different sessions in the past will produce different recommendations, right? Because the hidden states will be differently initialized. We use all the same tricks that we used in the initial recurrent neural network to train this session parallel mini batching, ranking loss functions, etc., output sampling. No? So that didn't change much. And we used two data sets again, one from job postings. This was actually the Rexis Challenge 2016 data. And again, the data from the online video site. And let me see here. Yeah, so, and we used a couple of baselines, personalized popularity, item similarity, again, the simple session-based recurrent neural networks, and recurrent neural networks on the concatenated sessions of the user. And then the two versions of the hierarchical recurrent neural networks. And yeah, so here the results. So you can see on the sync data, actually personalized popularity is really, really hard to beat. Turns out users always return to the site and click on more or less the same job postings. But at least on recall, the hierarchical recurrent neural networks are doing better, right? And really, really close on MRR at 5. But the results on the video are much, much better. So personalized popularity or item similarity here is about 0.4, and the hierarchical recurrent neural network reaches almost 0.6, right? So quite a significant jump here. So let me see, yeah. And it turns out that this version of the RNN here didn't really work here on the videos very well at all. So while we were working on this, on all of these models, there was quite a bit of literature published on recurrent neural networks for session-based recommendation, and it turned out that many of these models that were published were significantly outperforming our previous model without any additional features, etc. So we had a look at our original model, and tried to improve upon a couple of things that we thought were weak. And one of the main issues, turns out, was that the way we were sampling the output was not really optimal. We were sampling the output based on the other items that were clicked upon by other users, right? And using these items as negative feedback for the ranking loss functions. This is essentially like sampling the data distribution, right? Which, as we know, is, in most of this data, you have really long-tail data distributions, right? And this was creating all sorts of issues. One of them was, of course, once you sample the data distribution, your model might not become very good in scoring long-tail items, which is essentially the majority of items. And the items in the mini-batch essentially are not enough to train your loss functions very well over the mini-batches, right? Because you only sample clicked items. So one fast way to fix that is sample additional negative items, just uniformly, right? So you still sample your data distribution, but you add to this data distribution uniformly sampled items, right, from the data. And it turns out that this was a big help, right? So essentially you get the best of both worlds in some sense. We used again this two pairwise loss functions. But we also changed them a little bit. So basically, we took a smooth approximation of the max operator of the negative samples and used that in this loss function, what we call now the max Bayesian personalized ranking and the max top 1. And it turns out that with this kind of trick, you get gradients of higher magnitude, right? So this is the gradient based on the rank of the negatively sampled item. Okay, and these are the red and blue are the old loss functions, and purple are the new. Purple and green are the new loss functions. Okay, and turns out also that the results are quite significantly better. So let me see, these are the two loss functions with a new sampled approach. And this is categorical cross-entropy, which when you apply this trick also seems to work quite well. It wasn't working quite well when we are using only popularity-based sampling. And this is the old performance of the model. So, yeah, and here, basically more or less the same plot. No, here, sorry, this is the training time, and you can see that this is the training time without additional samples, right, for the loss functions, and you can see that essentially there's little change even when you sample 2,000 additional items per mini batch. The reason being that most of the time spent copying data between the GPU and the main memory, and so the additional sampling doesn't create any overhead there. Right. So yeah, and these are basically the best performances we got with this new technique over the initial RNN initial session-based RNN model, right? So we get between 20 and 30% better performance just by using this sampling trick. Okay. One problem that we came across when dealing with these models is that these models tend to be extremely large. And they tend to be extremely large for, let me go directly, for one reason. The reason being that when you serve recommendations, your input space or your output space has to be extremely big. Right? You have hundreds of thousands or even perhaps millions of items to serve. So your softmax on the output or your one-hot encoded input will be extremely large, right? So you can fastly run out of memory on even a GPU of several gigabytes of RAM. So what can you do? Well, yeah, actually the proportion, we actually measured that on our model, and on the session-based models, 99.9% of the memory was used for these two layers, actually the input and the output layer, right? So an obvious solution would be to try to shrink these two layers, right? The input and the output layer. Enter Bloom filters. Who knows what Bloom filters are? Okay, quick introduction. Basically, a Bloom filter is a way to recognize if a element in a set is there or not, right? The way it works is, let's say you have these words here. You have several hash functions. You hash these words into bins here on this vector, into buckets on this vector. You take another word, you hash it with the same hash functions. If you get collisions on all the hashes, the word is probably there. If you don't get collisions on all the hashes, the word is probably not there, right? So you cannot have any false negatives, right? But you might have some false positives based on how many, based on your hashing space and the number of hash functions you're using, right? There's you can actually compute the probability on that. Okay, so the way we use this Bloom filters for shrinking the input and the output layer is by performing what we call Bloom embeddings, right? We define a dimensionality that is smaller than the number of items that we have, m, right? And we take k hash functions, k hash functions h, and we take essentially the one-hot encoded item representations that live in a much larger space, right? The space of number of items that we have, and hash them down with these Bloom filters to a dimensionality of m. Okay? So, so that's then very trivial to use as an input. Okay? We have now this m-dimensional vectors that are a hashed down version of our initially one hot encoded items, right? And we can train also on the output with the same m-dimensional vectors, right? But once we've done that, we can also recover the probabilities for the initially one hot encoded vectors by taking, by computing this log likelihood over the reprojected, over the one hot encoded vectors, where we check the probabilities in the positions for each item the hashes fall into in this m-dimensional vector here. Okay? So we get a vector of m dimensions with probabilities. We check on the original one hot encoded item which buckets we need to access for the probabilities to get the probabilities, and we compute this log likelihood. We recover this log likelihood from there. Okay, so we can actually recover the probabilities on the original space by using this trick. We tried this technique on several data from the movie lens, Amazon book reviews, etc., etc. And you can see here there are all sorts of different sizes in data sets and different sparsities here. And it turns out, let me go straight to the results. Oh yeah, we used a couple of autoencoders and LSTMs on this data. All sorts of different optimization techniques and evaluation measures. And we compared also with several alternatives, the original hashing trick, which works only in the input space, by the way, that is implemented in Wopal Rabbit, error correction output codes, pairwise mutual information, and canonical correlation analysis. And it turns out that let me see here. Yeah, so these are the results we got on just doing the Bloom embeddings and using different compression ratios here. Okay, and the white line here is the completely uncompressed model, right? Just doing nothing, just training with one hot encoded vectors. And yeah, here you have a very high compression ratio, here you have a very low compression ratio. And these different colors are the different data sets that we used. And it turns out that on some data sets, and on some compression rates from about 0.2 to no compression, the Bloom embedded filters, the Bloom embedded models seem to work better than the non-compressed models, right? We tried to find a basically reasonable explanation. The truth is we don't really have a good one yet why this happens. But you can see that basically more or less you can have a 5 times compression of the model without losing any performance or even gaining some, most of the times, right? And here basically the results compared to alternative methods, and on almost all the data sets and and different compression ratios, we perform better, right? And yeah, with that, I would like to close the talk.
So we have time for question. Is there any question?
Hello, thanks for the talk. I'm a little bit concerned about the evaluation process. Actually, I've seen that you've just worked on top 5 recommendation in your evaluation process. Did you try to go further, like more than 5? I mean, Because
Usually,
it's-
sorry, I think we use top 20 in most, maybe on the Bloom filters, you mean?
no, before Bloom,
Before?
before
Okay.
Bloom filters.
Oh, yeah, here. Yeah, we typically use,
Yes.
yeah, here
these
we
ones.
use top 5, but we typically use top 20, yeah.
Yeah,
if you
because-
check at the previous results, it was top 20.
I mean, the thing about session based is like it can be used in like e-commerce and stuff like this, which it's the whole purpose of the study.
More or less.
And mainly these items have temporal values, so sometimes they are there, sometimes they're not there.
Correct.
So going further than the top 10 and top 20 is crucial for us. So is it actually? Did you try going further than that top 20?
Yeah. So if you look at the results of the original paper, everything was top 20.
Okay.
So, and I mean, on these data sets, we didn't find a difference between top 5 and top 20 in terms of relative performance. Right?
Yes.
But if you look at this is all top 20, if I remember. You can, let me see here maybe. Okay. Yeah, but the original, yeah, exactly, top 20.
Okay.
Yeah.
Okay. Thank you. As a follow-up to this question, I'm sorry. The thing I was thinking about is like, have you tried going through like comparing implicit type of feedbacks and explicit type of feedbacks?
So we find that the value in explicit feedback is very, very low, and it's also very difficult to find sort of, and I think if I'm not wrong, it doesn't exist, explicit feedback on sessions, right?
Yeah.
So it would be difficult for users to sort of click an item and rate it immediately. Generally speaking, we don't really use explicit feedback, and I find the value of it relatively limited.
I mean, because at a certain point you were talking about going on users, comparing the session-based, I mean, against, let's call it user-based recommendation.
Yes.
So did you go? Does it? I mean, data linkage doesn't bring anything to you? Or?
I see what you mean. So taking additional information from ratings, etc., and trying to sort of personalize further. We haven't tried that, but that might be an interesting sort of.
Okay.
Yeah.
Thank you very much.
You're welcome.
Any other question?
Have you considered the possibility of using convolutional nets as an alternative for RMS?
You mean as a sequence prediction model?
Right.
Yes, we're actually working on that right now. Yeah. There's nice work, by the way, on sort of using convolutional networks to simulate the way a recurrent neural network is working. They're called quasi-RNNs, and they work much faster than the normal recurrent neural networks, right? Yes, that's at least one advantage. Yeah.